As an application of Born approximation, today we are going to see the scattering by a very important potential which is called Yukawa potential. Actually, when you study the nuclear physics, then you find the utility of this Yukawa potential, particularly in discussing the nuclear force. So Yukawa potential is a well-known and very important potential. Okay. So if a beam of particle will incident on a scattering center which provides Yukawa potential, what will be the differential scattering cross section and the total scattering cross section if we apply to calculate these quantities in accordance with the Born approximation? That is our today's problem. So a question in examination will be asked, discuss the scattering by Yukawa potential in Born approximation. Okay. So first of all, definitely we have to know how this Yukawa potential is defined, and taking its definition, then we will apply Born approximation to find the scattering amplitude, and once you get the value of a scattering amplitude, then we can easily find the differential scattering cross section, and if differential scattering cross section is known, we can find the total scattering cross section. So now let us start to discuss this problem. Yukawa potential is defined like this. This is V of R equal to V naught times e to the power minus R over capital R divided by small r. Actually here this capital R is a constant term. You can also take this 1 over R equal to alpha. So this Yukawa potential in several textbooks is defined like this. This is V naught e to the power minus alpha R over R. Okay. This is the basic definition of Yukawa potential. Now, taking this potential under account as a scattering potential, we have to find the scattering cross section if a beam of particle gets incident on such a potential field. So now let us start how the scattering amplitude is defined in Born approximation. And we have learned this thing several times earlier. The scattering amplitude in Born approximation denoted by the symbol f of theta phi is defined as minus m over 2 pi h bar square integral of e to the power I kappa dot r dash times v of r dash d tau dash. Here this kappa is what? This is k minus k dash, and k is the wave vector for the incident beam of particle, and k dash is the wave vector for the scattered beam of particles. Actually, if you will multiply this kappa by h bar, then this actually gives the transfer of momentum, just because this will be equal to h bar k minus h bar k dash, and h bar k actually represents the momentum of the incident beam of particle, and h bar k dash, this is the momentum of a scattered particle. So h bar k minus h bar k dash, which will be h bar kappa, that is actually the transfer of momentum from incident particle to the scattered particle. Okay. Now we will actually evaluate this integral in a spherical polar coordinate system. Now you also know if the scattering is elastic, then the magnitude of the wave vector of incident particle and that of the scattered particle are equal. And in that condition, if theta is the angle between the vectors k and k dashed, then this kappa will be equal to mod of k minus k dashed, and that will be equal to 2k sine theta by 2. Actually, this result you have seen earlier several times. So I think now it is completely in your mind. Okay. Now, if you take that this kappa vector is along the polar axis, that is along the z axis you can say, and this is the direction of vector r dash, and the angle between them is theta dash. Actually, you can also take this angle theta, but for integration purpose we will write theta dash, r dash, phi dash. Okay, but finally you can replace it by r theta phi. Okay, so in that condition, you know, kappa dot r dash, this will be kappa r dash cos theta dash, and this volume element d tau dash, which is also written as d3 r dash. This is also written like this. This is given by r dash square dr dash sin theta dash d theta dash d phi dash. Here actually you can also take r theta phi without writing dash symbol. We can use this result. Okay. Now taking these things under account, you can evaluate this integral, that is integral of e to the power I kappa dot r dash times v of r dash d tau dash. Let us see. This will be integral 0 to infinity r dash square v of r dash dr dash. This is actually the function of r. So I have separated, and you know limits for r is 0 to infinity. Now write the function of theta. This will be integral 0 to pi, because limits of theta is 0 to pi, and this is e to the power I kappa r dash cos theta dash sin theta dash d theta. Okay, and the integral 0 to 2 pi d phi dash. And you know, integral of d phi dash 0 to 2 pi, that is simply 2 pi. So this has been written here. And the first integral is at each, here you can see. Okay. And now this second integral, I have just evaluated this integral by taking each and every step in my previous video on the scattering by an attractive square wave potential in Born approximation. So I have written its value here directly. You can watch my previous video where this integral has been calculated by following each and every step. Here actually we consider that this cos theta dash is equal to t. We have considered a new variable. And then you will take its differential minus sin theta dash d theta dash will be dt, and then you will find the limits for this t, and that will be actually plus 1 and minus 1, and for removing the minus sign, limits actually gets interchanged, and then you have this result. Okay. Now in fact when this integral will be evaluated, this will be in the form of e to the power I kappa r dash t minus e to the power minus I kappa r dash t and divided by I kappa r dash. You can watch my previous video as I have told you for evaluating this integral. And then you use the formula for sin theta equal to e to the power I theta minus e to the power minus I theta divided by 2i. After using that formula, you get this integral comes out 2 times this much. Okay. So now this integral becomes 4 pi over kappa times integral 0 to infinity r dash v of r dash sin kappa r dash dr dash. Okay. Now we will use this value of integral which we have obtained in this equation 3 in this equation 2, which defines the scattering amplitude in Born approximation. So now you can see the scattering amplitude actually is only a function of theta, not of phi. In general, it may be a function of phi. So previously I have written the symbol f of theta and phi. But now I am writing only f of theta, because now it is found that this f is only a function of theta in this case. Okay. And so f of theta, after substituting that value, you will get this is minus 2m over h bar square kappa times integral 0 to infinity r dash v of r dash sine kappa r dash dr dash. Okay. So in this way, we have obtained the expression for the scattering amplitude if the scattering potential is v of r dash. Now if you know the actual meaning, actual value of this potential v of r dash, you can evaluate this integral for getting the value of a scattering amplitude. And after that, you can obtain the differential scattering cross section. Now, as you know, that differential scattering cross section, which is denoted by the symbol sigma of theta or d sigma by d omega, this is actually equal to a square of the modulus of a scattering amplitude. Okay. So this will be a square of f of theta, mod of f of theta, and f of theta is defined here in this equation 4. So let us substitute that value, and after that you get d sigma by d omega is equal to 4m square over h bar 4 k kappa square, and a square of the modulus of integral 0 to infinity r dash v of r dash sine kappa r dash dr dash. Okay. Now actually in the present case, as we have to find the scattering cross section by the Yukawa potential. So now recognize this potential v of r dash as Yukawa potential. And you have just seen earlier that this Yukawa potential v of r is defined like this. This is v naught times e to the power minus r small r over capital R over small r. Okay. So now let us substitute this value of potential in the expression for this differential scattering cross section at the place of v of r dash. Now as I have told you, you can write r instead of r dash, you can write theta instead of theta dash, you can write phi instead of phi dash. Okay. So here I am not writing now r dash, but instead of r dash now I am writing r. Okay. So when we will substitute this value here, it will get a squared, and so v naught square is a constant factor, so it will be outside of the integral, and therefore d sigma by d omega, this is 4m square v naught square over h bar 4 kappa square, and the square of the integral 0 to infinity e to the power minus r over r sine kappa r dr. R dash has been replaced by this r. Now we will try to evaluate the value of this integral, and it can be easily evaluated. Now let us see. See the evaluation of this integral. Okay. You can see the factor e to the power minus small r over capital R is at each. And you know, instead of sine kappa r, we can write e to the power I kappa r minus e to the power minus I kappa r divided by 2i. We can write. Now, let us multiply by this exponential factor e to the power minus small r over capital R to the exponential factors inside the square bracket. And you can see our result will be 1 over 2i integral 0 to infinity e to the power minus 1 over r minus I kappa times r dr, and minus 1 over 2i integral 0 to infinity e to the power minus 1 over r plus I kappa times r dr. Okay. Now these two integrals are very simple. This is in the form of e to the power ax, and that is e to the power ax divided by a. So the first integral is 1 over 2i e to the power minus 1 over r minus I kappa times r divided by minus 1 over r minus I kappa, and limits are 0 and infinity. You can easily understand. And the second integral, this is minus 1 over 2y times e to the power minus 1 over r plus I kappa r divided by minus 1 over r plus I kappa, and limits are same 0 to infinity. Now, when you will put the upper limit infinity, you can see due to this minus sign present in both of the terms, the first term will be e to the power minus infinity, and that will be 0. So, first term will be 0. And when you will take r equal to 0, then numerator of both of the terms will be 1. Okay? And in denominator, there will be minus 1 over r minus ik. So that will become plus. So the first term is 1 over r minus ik. And the second term will be 1 over r plus I kappa. Okay. Now, when you will take LCM and simplify, your result becomes like this. This is kappa over 1 over capital R square plus kappa square. So, in this way, you can see we have evaluated the value of this very integral. Now, after getting the value of this integral, let us put this value in equation 5 to get the value of differential scattering cross section. Okay? You can see, apart from this integral, the multiplicative factor in this equation 5 for the expression of d sigma by d omega is 4m square times v naught square over h bar 4 times kappa square. Okay, so let us use this result. And you can see this d sigma by d omega, that is the differential scattering cross section, is given by 4m square v naught square over h bar to the power 4 times 1 over r square plus kappa square whole square. Okay? And when you will put this kappa is equal to 2k sine theta by 2, as we have seen earlier, then after substituting this value of kappa, the expression for this d sigma by d omega becomes 4m square v naught square over h bar to the power 4 times 1 over r square plus 4k square sine square theta by 2 whole square. Okay? So this is the expression for the differential scattering cross section. And you can see the value of this differential scattering cross section depends on this value of capital R, the constant R, the value of constant V naught, and most strongly it depends on the angle of a scattering theta. Okay? With change in theta, this differential scattering cross section will change. Now, I have here mentioned a homework for you. If you find the differential scattering cross section for Rutherford scattering, that is taking the potential V of R equal to Z1 Z2 E square divided by R. This is called Rutherford potential. Then you will find the differential scattering cross section. You will see if we will find the value of this Yukawa, you find the differential scattering cross section for Yukawa potential under the limiting condition R tending towards infinity, then you will see this result defined in equation A becomes identical to the differential scattering cross section obtained in case of Rutherford scattering. And I have not done the algebra here. This is just a homework for you. You can try it. Okay? Now, after getting the expression for this differential scattering cross section d sigma by d omega, now we can easily find what will be the total scattering cross section. You know, the total scattering cross section sigma is given as integral of d sigma by d omega times d omega. But you know, d omega is equal to sine theta d theta d phi integral. But integral of d phi is 2 pi. So you can say that this d omega is equal to 2 pi times sine theta d theta. So instead of d omega, I have written 2 pi times sine theta d theta. Now, d sigma by d omega, we have already obtained in this equation A. So now let us substitute this value of d sigma by d omega here and try to evaluate the integral. So sigma will be 2 pi times this much integral 0 to pi, because limits for theta will be 0 to pi, sine theta d theta divided by this much. Okay. Now if your aim is to evaluate this integral, then I am just giving you a hint. I have not done all the steps, but I am just giving you a hint. So for this, you put we introduce a variable x, and let us say this x is related to this capital R by in this manner. By x is related to theta in this manner, x equal to 2kr sine theta by 2. And so that when you will take sine theta d theta, then you will see this will come out to be x dx over k square by r square. Okay. So using this value and taking the proper limit when theta is 0, theta is 0, then what will be actually x? You can see when theta is 0, x will be also 0, because theta 0, it means sine 0, and that will be 0. And when theta is equal to pi, then x will be what? 2kr times sine pi by 2. But sine pi by 2 is 1, so x will be 2kr. So the corresponding limit for x will be 0 and 2kr. Okay. And instead of sine theta d theta, we will write x dx over k square by r square. Here there is k square by r square, and here is x dx, and divided by 1 plus this much. But you know, you have assumed that 2kr sine theta by 2 is x. So this 4k square r square sine square theta by 2, this will be simply x square. So this is 1 plus x square whole square. Okay. Now after integrating this, your result will be sigma equal to 16 pi m square v naught square r4 divided by h bar 4 times 1 over 1 plus 4 k square r square. Okay. But you know, k square is 2me over h bar square. You have used this result several times while studying the Schrodinger wave equation. So when we will replace this k square by 2me by h bar square, where E is actually the energy of the incident particles, then the total scattering cross section sigma is given as 16 pi m square v naught square r4 divided by h bar 4 times 1 over 1 plus 8 me r square divided by h bar square. And this is the expression for the total scattering cross section when the scattering takes place by the Yukawa potential, okay, in accordance with the Born approximation. And you can see that this sigma, that is total scattering cross section, again depends on the energy of the incident beam of particle. If energy E is larger, you know, Born approximation is applied particularly in the case when energy is larger. If E will be larger, then this term 8me r square over h bar square in denominator will be larger, and so that the cross section will be smaller. For larger energetic beam of particle incident on the Yukawa potential, the cross section will be smaller. Okay? So I hope you have clearly understand how we can calculate the differential scattering cross section and the total scattering cross section in Born approximation by Yukawa potential. Okay, thank you very much.